Hello and welcome back to our class of Foundation Engineering. So today we are going to do another example of triaxial test and try to complete the section about soil strength, but still on chapter 1, which is review of soil mechanics used in foundation engineering. Okay, so that one is because last time we did I think one example about triaxial test, how to obtain the soil strength parameters from triaxial test. Okay, this time we'll do another example, but this example in this video is for UU test, triaxial test. Okay, and after that we will talk about unconfined compression test. That one also is used sometime because it is very simple, a very simple test, and can give us some information on the soil strength. So previously we did example on this one, CU test, CU triaxial test. I hope you remember the meaning of CU triaxial test. Okay. So confined and undrained triaxial test. So in this example, in this video, we'll do an example on this UU test, unconfined and undrained test, triaxial test. Okay. So here is the example actually. So it's same here, same figure, triaxial test. Assume if you assume that one wish to determine the strength property of medium stiff clay foundation under short terms mean undrained condition. Always, if you are dealing with clay in short term, if the time is short, the clay will not have enough time to drain water. Okay, in that case, it has to be undrained condition. That is very important for you to understand. So the most effective method to achieve this is to conduct the UU test, which is quick test actually. So U unconfined and undrained triaxial test. Okay. So we will take a result from a test, a UU test, to estimate the undrained strength parameters of soil. This table. Okay. So two tests were done. The test number 1, the cell pressure, means the pressure from the cell fluid, this inside in the fluid, is 40 kPa, and the deviator stress at failure is 102.2 kPa. I hope you remember the meaning of this deviator stress. It means just the difference between the major principal stress and the minor principal stress. So sigma 1 minus sigma 3, that is, so the pore pressure was not measured. That's why you see Na here. The second test is, the result for the second test are here, 60, 101.4, and none here. So one remark in this UU test is this one. As you can see, this is almost same in both tests. The first test is 102.2. The second test is 101.4. Almost same value for these derivatives. That is the signature of UU test actually. So it means that even though you add load, any load you will add will be taken by the water. The water will support it. I will explain this more later, but this is what changes, what makes difference between the UU test and this one CU test we did before. Okay, yeah. So if you remember in the previous example, the previous video, these value were not same. Okay, so I put the table here because we will need it to continue the example. Okay, the objective is same. We want to compute the strength parameter based on this triaxial test result. So in this test, the two tests we did, we have here in this example, the pore pressure generation is not recorded, not monitored. So I didn't even present it here in this table. Okay, and the total stress must be plotted as here. The total stress is plotted here, this figure actually, not 10, but figure 11. Okay. Slow. So this table 3, we will explain later how this figure is obtained. Okay. So this table 3, this table, we can see that, as I said, the deviator of stress, it doesn't change that much. It almost same. Okay. While we can see that the cell pressure is changing. And as I said, this is the signature of the UU test. This is because in this UU test, there is no drainage. If you are not draining the water, it is undrained. So it means the soil sample you have in your test is not consolidated. Okay. So the soil structure, the soil particles, they are not affected at all. No matter the load you are adding, the load is taken by the water because you are not draining the water. So it's like you put something in a container that contain water and you try to press it. No matter the force you will bring, the external force will be taken by the water. It will not touch, it will not affect much the soil you have in the container. This is why this derivative of stress does not change. Okay. So the strength parameter obtained from this figure. How you obtain this figure? Because if you take the the first test, for example, you have deviator's test is 102. This is just the difference between the first sigma 1 and sigma 3. I have explained this before. So the major principal stress, sigma 1, minus the minor principal stress, which is sigma 3. So sigma 1 minus sigma 3 gives you this deviator stress. And I also explained that sigma 3 is only this one. The sigma 3 is equal to the cell pressure. So for this first test, 40, it will be here. And then if you want to have the sigma 1 on this axis, you just add from 40, you go 102.2 more. So it's just addition. So it will be 142.2. That's why you will be around here. 100 is here. As you can see, the steps, 1 is around 10, I think. So 80, 90, 100, 110, 120, 130, 140. So point 140, and then the next one is 142.2. Okay, so this is the first test. There's the second test. Here, 60, you start 60 here, and you add this value. Okay, by adding this value, 101.4 around here, because it will be 60 plus 101. So it will be 161.4. It will be around here. Okay, so you get a second circle. So don't forget that this is just the diameter of your circle. The deviator stress is the diameter of the circle, the Moore circle. In that case, it means no matter the number of tests you will do, the diameter will not change. It will be about same. Okay. If you get the cell pressure around here, then you'll get another circle which will have same diameter. As a result, the slope to all these circles is like just horizontal line in difference. So I just suggest you to, if you didn't see the previous video, watch the previous video and come back here and see the difference. Okay, these circles are like that. So as I told you previously, the friction angle is just the angle that make this tangent with the horizontal axis. So as you can see here, this one is 0 because this is parallel. This tangent is parallel to the horizontal axis. Okay, and the cohesion is just the value here where this line will, the cross section, this line and the vertical axis. So that will make the cohesion here 50.6 kPa. Okay, so that's why we can obtain this value as the strength parameter. Okay, I will explain you why we need to put we put U here, but you can just put C also. Cohesion is 50.6 kPa, and the internal friction angle here also we add U is 0. Okay, so I hope you understand how to draw the Moore circle and how to obtain the parameter. You just need sigma 1 and sigma 3, and then the difference means the deviator stress will give you the diameter of your circle. You draw it in that one. Okay, and you draw the line, a line that is tangent to both circles at the same time. Please don't tell me that the line can be this. If you do that, it will be tangent to this first circle, but it will not touch this one, never. The only way that this line can be tangent to both circles, or even you do more and more circles, it only this horizontal line, which is parallel to this axis. It means that phi is 0. So why we are adding u to the result? You see u here, cohesion, and we add u. The phi also we add u. The reason why we add u is to distinguish the UU test parameters. Okay, so if you see CU or phi u, it means these are the result, these are the same parameters from the UU test. That's why we are using the U to distinguish. Okay, so under UU condition. So in that case, if we use this equation, do you remember this equation? This is equation for the sharing strength. Okay, how the capability of the soil to stand against sharing. Okay, so in this case, since this phi, in this case phi is 0, if you try to calculate this sigma, this tau f, the shear strength of the soil, you will see that this term will be 0 because tangent 0 is 0. That is, I hope everyone knows that. Okay, phi is 0. Sorry, today my pointer is not working well. I don't know why. But since phi is 0 here, then tangent phi will be 0 also. So this term here will be 0. So it will remain only cohesion. Okay, but since in the UU test, the cohesion is called CU. That's why we will have shear strength equal CU, which is here. Okay, this is what we have here. Okay, yeah. So tau f slash u, it means for UU test. Very strange. My pointer is not working. Yeah, anyway, I hope you can follow me and you can understand what I am saying. Okay, let's try to progress. So the most critical foundation design scenario presented by saturated, slow drains soil, such as clay and silt, involve undrained condition. Okay, this is prevailing immediately after the foundation is constructed. So it means that if you are having clay and silt, saturated clay or silt, that you have you will have undrained condition, like immediately after the foundation is completed, if you are doing foundation on this type of soil. Okay, so in that case, the undrained shear strength SU, if you want this one, you can say it's SU also. The undrained shear strength is typically used to design the foundation on the soil. Okay, so if you are designing your foundation, in this case, you went on your construction site and the lab test or field test has shown that the soil you have on this site is clay or silt. Okay, under this foundation, it's better for you to consider that the shear strength of your soil on the construction site is the undrained shear strength one, and you ask the lab to give you to do the UU test and give you the value. Yeah. Okay. I think for the triaxial test, this is the last slide about the triaxial test is. So I hope we have covered everything and you you have got some knowledge on it. Now let's move to unconfined compression test. That is also another alternative to obtain the soil strength. Okay, so that's why very often some people find it very convenient to use the unconfined compression strength to express the undrained shear strength. So if you cannot do the UU test of clay soil, you can do this unconfined compression test. This is something like that. You make, for example, this is clay. You make the sample, the soil sample, like cylindric like this, and you place it here, and you can apply load. You get load and deformation. The clay will deform like this. Okay. So this test can be used to determine the CU. Do you remember what is CU? The previous slide. The undrained cohesion, which is the undrained, at the same time, the undrained shaft strength. Okay. We can use this test to obtain the CU. And here, I will explain you how we can obtain the CU. But it obtained by measuring the unconfined compression strength just from the compression, because we will apply load on the sample here, and the strength from the compression test will be used, which is QU, will be used to obtain CU. And the formula for that, I will tell you soon. So because this test can be visualized as undrained triaxial test with no confining pressure, so the more circle for this test for condition are same as the unconfined, as the UU test. So you will have more circles like this. Okay, you have 0 here and QU here. This, based on this, as you can see here, the diameter, the value of the diameter of this circle is QU. Okay, and the radius of the circle is CU. In that case, it's very simple. You can obtain the CU by just doing this, dividing the compression strength by 2. Okay, CU is half of QU, and the formula is here. That is very simple, actually. So if you cannot do the UU triaxial test, you can do this, and the compression strength of this sample will be equal to the undrained shear strength. It will be equal to CU. Okay. Very simplified method. So same the sample, the same triaxial apparatus also can be used. They're saying they can be used the same triaxial apparatus to do this test, but this is mainly how people do it. This example here, illustration here, from A, B, C to D. Yeah, the only thing is now when you are compressing, because we wanted the test the value in kPa. Don't forget that the applying, you are applying force on the sample. So you need the pressure, the stress. So you have to do the force divided by the section, the cross section of your soil sample. Okay. But the problem here is this soil sample, the cross section is changing when you are doing the compression. So it has to be corrected. Okay. So let's say just one example here. I will take the opportunity in this example to show you how to correct the cross section of the soil sample. Okay. So we have here one table, result of a the unconfined compression test. Okay. So we want to determine the compression strength, and then as the formula say, from that compression strength we can get the undrained shear strength, means Cu, which is just dividing the compression strength by 2. Okay, these are the result of the test, and you have here displacement and the force, and you have here the strain, and the stress is here. Just don't forget that stress is force divided by surface, and the force is here. The force is as given here. The force, the surface will be just the cross section of the sample. Okay, so since what I said before in the previous slide, the cross section is changing when you are applying load. Okay, so it must be noted that this cross section modified for each test stage has been used in in, comp in computing the stress basis based on the following simple relationship. All this to say that since the cross section of the soil sample is changing, you have to correct it for each displacement, for each deformation, for each strain here, based on the strain. Okay. Here, for example, if when you are applying the force, you see this cross section here will not be the top and the bottom. For example, you can see it's different. So you have to correct for each step. For example, step number 1, you have to do the initial cross section divided by 1 minus the strain. Okay, before you proceed. And this is just to explain you how the test is working itself. It not you will not consider the same cross section for from the beginning to the end. Okay, anyway, you obtain the stress here, and the strain. Yes, strain and stress. I hope you know how to estimate strain. Okay, this displacement divided by the original length, then you get the strain. Okay, displacement and strain is not same. That they are not same. Displacement and strain are not same. But that I hope you know how to estimate that. If you don't know, let me know. Displacement divided by the total length of the sample will give you the strain. Okay, And stress is obtained by dividing the axial force by the cross-section. Corrected cross-section. Correction is done with this formula. So after doing everything, this table, by using this table, you can draw this line, for example. Horizontal axis is strain. So this strain, not displacement, please, strain. And the stress is here by using force divided by cross section. So based on this graph, this figure, we say that the unconfined compression strength is 320 kPa, 320, it around here, which is just the maximum this curve, because after reaching the maximum, we see it is not strong anymore. The sample, the strength, the strength is becoming weaker and weaker. Okay, so the maximum here should be taken as the strength 320 kPa. This is the maximum stress that the sample can support. See, after that, above that, it will decrease. You will have larger displacement for small increase of the stress. Okay, 320. So according to the formula, this formula, we can obtain our Cu by just dividing this compression strength by 2. In that case, we can get our, we can get our undrained strength, mean Cu, as 160, which is just half of this 320. Okay, that is very simple. So this is the end for this part of the chapter. The part, not this part of this chapter, means next video we will start the section 1.5 of this chapter. This is section 1.4 about strength of soil. And this part is somehow very important for foundation engineering. Please, yeah, you have to understand everything about this section, the strength of soil, because this is the only way you know if your soil will support your structure, foundation. Okay, yeah. So that's all for this video. Thank you very much for your time, and see you next time.